Okay, hello. So if you're seeing this, we're learning about circular motion, and I may or may not be there to instruct this because I may or may not have jury duty. So bear with me as we are going to do this screen sharing style um, over Zoom. So here we go. Start. Okay. So what I'm going to do is I'm going to scroll through the slides and explain each one as if I was there in class with you. And hopefully I'll turn this into an ed puzzle and you'll be able to answer questions. And this will be somewhat like as if I was there. Okay, so to start, what is velocity? So we've talked about velocity a lot so far this year. So what is our formula for velocity? So take a minute to think about that. And I will write it. Oh gosh, not that big. So velocity is equal to distance all over time. So we know that the distance an object travels, or the change in distance over the course of time it takes. So we know that. Acceleration, we know. So first take a second to think about what it is. So acceleration is our change in velocity all over time. So we know that velocity, though, is dependent on distance over time. So we can also write our acceleration formula as distance all over time, all over time. Okay? So that's another way we can write this formula. So mass, we remember, is measured in what units? Think about the units. So it's measured in kilograms. And then finally, force. Think about what force is equal to. So this is also similar to this formula, but rewritten as m times a. So force is equal to mass times acceleration. So we can also write this as, since we know acceleration is equal to delta v over t, so we can write force is equal to mass times delta v over t. But then we know that the change in velocity is also equal to our distance over time, so we can also write this as mass times distance all over time, like that. Okay. So moving on from our review, one more thing. What are our units for all of these? So we know distance usually has units of meters, time is seconds, acceleration, so we know that's meters per second all over seconds, so it would be meters per second squared. We got kilograms. Force, our unit is, think about this for a second, newtons, or N. Okay. All right. So we just went over all of these. So we already know velocity is the measure of change in distance over time with direction. So remembering that velocity is a vector. Speed is a scalar. And then mass is the amount of matter an object has. Acceleration, the measure of the change in velocity over the change in time. And force is a push or a pull that is equal to the mass of the object multiplied by acceleration. So that's just putting force is equal to mass times acceleration into words. So just more words. So just to review. Okay. So on to our new concept here. So talking about uniform circular motion. So uniform circular motion is defined by any object that is moving at constant speed in a circular path. Okay, so think about what constant speed means. What does speed, how does speed differ from velocity? So speed does not have direction. So that's why it has a constant speed. Okay, so determining speed. So we know that our formula for velocity is distance over time. And so if an object is traveling in a circular path, it's traveling the whole circumference of a circle. So think about, if you think all the way back to when we first learned about the formulas for circumference, radius, all that stuff, you have I have no idea if you can see me doing this with my pencil, but you have your radius here, and then it sweeps out the circumference, right? And it fills the whole area. So the circumference is equal to 2 times pi times r. So since it's transferred a little weird here, the distance an object in moving in a circular path is equal to the circumference. So you need to remember circumference is equal to 2 pi r, where r is the radius. So if you're taking notes, I would write down, let me highlight it. Let's highlight it in yellow. I would take, ooh, that's small. I would emphasize this part. And then also, actually, all of this stuff is important here, especially this stuff at the end. Anyhows, so the time it takes an object to complete one revolution is called the period. And so we represent period as a symbol of a capital T. So I think like I Googled it. Did I Google it on my iPad? Like period with a T. I think that's like a saying that they, like a slang thing that they say. So when you see, when it's asking about a period an object takes to travel on the circle, think of it as period with a T. And remember that it's a capital T, but also it's the time it takes an object to complete one revolution. Okay. So then we can say, so if we know T, capital T period, that's going to be equal to kind of like really, no, I don't write that. But okay, never mind. So from there, we can write that velocity is equal to distance over time. So we know that because we're now translating it to what's the velocity of an object traveling in a circle. So the distance, it's traveling the circumference of the circle as it's going around. So we're going to use 2 pi r for our distance. And then t, that's just period. We're going to put in the time it takes the object to make one revolution around the circle. All right, so let me write this a little bit better for y'all. So velocity for circular motion, or centripetal velocity, is equal to 2 pi r all over period, which is capital T. Okay, so r is the radius, capital T is period. Okay, all right. So onto an example. So a 1,500 kilogram race car takes 1 minute to complete one lap of a circular racetrack with a radius of 400 meters. Determine the speed of the race car. So first things first, we always write out our knowns, which I know they're literally there on the screen, but we're going to write it out because we need to practice that. So we know the mass is 1,500 kilograms. The time it takes to complete one lap of a circular racetrack. So this is tricky. Do we think this is time or period? And what makes it different if it's not time? So think about that. So this is a period because it's 1 minute to complete one circular lap. To complete the lap, it takes 1 minute. So we know t is going to be equal to 1 minute, our period's 1 minute. And then finally, our radius is equal to 400 meters. Okay, so this formula here came from the slide before. So we know that 2 pi, which we know is just our circumference formula, all times the radius, which we know is 400 meters, all over the 60 seconds because we do not use minutes in our units. So plug that into a calculator and you should get 42 meters per second. So really, the only difference here is we have an extra step because distance isn't just the radius, it's that times 2 pi. So we have to think about remembering our circumference. All right. So if an object is moving at constant speed in a circular path, can it be accelerating? So the answer to that is yes, although the speed may be constant, the direction is changing. So technically, velocity is always changing when an object is moving in a circular motion. Therefore, there's always an acceleration. But remember, a few slides before, we said it was moving at a constant speed. But remember, that's because speed is a scalar, velocity is a vector. Okay. So if direction is changing over time, then velocity must be changing. So acceleration is the change in velocity over time, delta v over delta t. So if velocity is changing over time, then the object must be accelerating. Now, think for a minute. If the velocity is always changing directions, what way is acceleration always pointing? Think about it. Okay. So we'll get to it in a second. So note that the velocity vector is at the right angle to the position vector. So it's always tangent to the circle at any given point. So we've seen some, and I will also assign a simulation that will demonstrate this, that if this vector was going around the circle, it would always be tangent to the circle and make a 90-degree angle with this vector here. So let me try and draw it a little. So 90, and then here we see 90. But what if our radius was here? Call that R3. Do we think velocity would be pointed this way? I don't think so. I think it would be pointed straight tangent that way, and it would be 90 degrees there. Ooh, I was batting the arrow. All right. So, and we know velocity is equal to the change in radius over time. Okay. So centripetal acceleration. That's a fun word, right? So centripetal acceleration, or that's supposed to be a lowercase a with a subscript of c. This transferred weird. So the acceleration of an object, going back to the question I asked a few minutes before, the acceleration of an object moving in a circular path is always pointed towards the center of a circle, and it is always perpendicular to the velocity vector, which we should kind of remember that from a little while ago. So we know acceleration is the change in velocity over change in time. And so we also need to remember that when we have a change in velocity, when we add these vectors of if there's two velocity vectors, we have to account for the angles that they make between them. Okay. So the angle between the radius 1 and radius 2 are the same as the angle between the vector 1 and vector 2, or velocity 1 and velocity 2. So therefore, the triangles these vectors make are similar. So you can say that they're all the sides. So this is just basically going through a proof. And the main takeaway I want you to know from this is that through all of this, we get to acceleration, centripetal acceleration is equal to velocity squared all over the radius. Okay. And if you have more questions on this proof, I would love to do it in class. Okay. So for centripetal acceleration, so an alternative representation for centripetal acceleration can be derived using the circumference and period of revolution. So remember our circumference, 2 pi over r. Distance is circumference, and then t, time, period. So a period is the amount of time it takes to make a 1 revolution. So substituting that into our equation from up here, a sub c, oh, it's actually right here, this equation. We get that plugging in for velocity, knowing that it's 2 pi r over t. We come to this, and then further going down. So these are all just plugging in from the time before and simplifying down the equation. And we see that the most simplest form when using radius and period is centripetal acceleration is equal to 4 pi r. I'm sorry, let me say that again. So centripetal acceleration is equal to 4 pi squared times the radius all over t squared. Okay. All right. So we just talked about acceleration. We talked about velocity, talked about radius, and we mentioned mass at the beginning. So we knew that force was going to come along somewhere. So to make an object move in a circular path, an external force must act perpendicular or at right angles to the direction of motion. So this force is called centripetal force. Okay. So the instantaneous direction of velocity is going to be in this case. So if we have an object right here, would be pointing straight up. The object is moving around the circle, and at this point it's tangent. Okay, so radius makes a 90-degree. However, our force is exactly parallel, pointed the opposite direction to the radius. So it's always pointed towards the center. So the force is pointed directly opposite. Okay. So centripetal force is affected by mass, velocity, radius. And so we know this because we remember our, let me write this in white, let me make this bigger. So we know F is equal to ma, and we know acceleration is equal to velocity over time. So we know that all of these things we have to account for. But using Newton's second law of motion, where we have centripetal acceleration, so going back to this here, we come to this final formula, that the centripetal force is equal to mass times velocity squared all over the radius. All right. So this equation should be given to you. You will never have to derive it or memorize it. So just kind of the notes before here were just how we got here. So we know that the force, mass, velocity, radius, velocity squared comes from our acceleration. Okay, we're gonna skip over this part. So think about this for a second. What is the cause of the force for these circularly traveling objects? So think about this first one, the Earth. Why does the Earth travel in an orbit? Why does Earth orbit the sun? Why in that circular-ish path? So that is because of gravity. So two objects have, the gravities are always the same. So they're always going to be equally pulling each other, which gravity is a force, towards each other, and that force never changes. All right. A race car traveling around a turn on the racetrack. Friction. So we've talked about how when you increase friction on one side, it can cause an object to turn. So an athlete throwing a hammer, think about this one. This one's tricky. So tension in the cable attached to the hammer. So think about if you're kind of like, if you're swinging a hammer, you're creating a circular path, and then you let it go at a certain point and it's going to go shooting in the direction you want. We'll do some labs to further explain that. Okay. So if the path, if the centripetal force were suddenly removed from an object moving in a circular path, what trajectory or path would it follow? So think about this object that's here on this path. So basically what we're saying is you're swinging an object, you're swinging it, and then all of a sudden you let go at a certain point in the circular path. Would this object continue going in a circle, Would it have a curved trajectory since it's been going in a circle? Would it shoot straight off? Would it defy logic and go backwards? So basically, let me draw some. Would it look like this? Let's call that T1. Or would it look like this? Let's call that T2. Or maybe do you think it would look like this or something because you're weird? T3. Just to give 3 options. So the correct answer is it would go take trajectory 2 here. It would go straight off because at that instant moment, you are removing the force that is causing it to travel in a circle. So now all of a sudden it has a force that's causing it to travel straight, going straight off. So this is because an object in motion wants to remain in motion at a constant speed in a straight line. So if the unbalanced centripetal force is removed, the object will continue in a straight line. So let me zoom in here. Let me ask you another question. Think about this one. So we have a circle. Let's see. There we go. And an object on the circle is right here. First, think about what does our acceleration and velocity vector look like? Think about that. So after you thought about it, we know, ooh, that's not towards the center. Here's the center. So we have acceleration going towards the center, and we call this A sub c. And then our velocity is tangent to the circle. Ooh, go away. So if this force is removed at this instant, the object will continue along. Let me do this in a different color. Let's not do blue because the screen's blue. It would continue on a path like that. Cool. All right, here is another example. So a 1.5 kilogram cart moves in a circular path of 1.3 meters radius at a constant speed of 2 meters per second. So determine the magnitude of centripetal acceleration, A sub c. Determine the magnitude of centripetal force, F sub c. And determine the period, capital T. Okay. So first, let's calculate our centripetal acceleration. So A sub c, which we know is velocity squared all over the radius. So we know we were given a velocity of 2 meters per second. So we just plug that right in. And that's squared. And then we are given the radius of 1.3 meters. So we just plug that in and we get 3.1 meters per second squared. So that is our A sub c, our centripetal acceleration. Okay, so now for centripetal force. So now we have our centripetal acceleration. So that should come in handy. So remember that our centripetal force is equal to mass times centripetal acceleration. So we were given up here, it's a 1.5 kilogram cart. So we're going to plug that right on in. And then all times our acceleration, centripetal acceleration, which was 3.1 meters per second squared. And so we plug that in and get 4.6 newtons, which is right here. Great. Okay. So finally, our final question here is, what is the period? So remember, our period is going to be, we can solve for a period from velocity is equal to circumference all over period. So by doing cross multiplication, we see that velocity times period is equal to circumference, which from there, we can see that period is equal to circumference all over velocity. but we know that circumference is equal to 2 pi times the radius. And then we also know we have velocity, so we're given that. So we have all of these values. So we have 2 times pi times our radius, which is 1.3 meters, which was given, and then our velocity, which was given right here, constant speed of 2.0 meters per second. So we plug it right on in, and we'll get our answer of 4.08 seconds. So cool. So that is our notes for centripetal acceleration, force, velocity, circular motion. So we will continue to do practice problems and labs for this. And if you have any questions, as always, email me.